Okay, so hi Rahul. So I guess I'll wait for like 4 5 minutes so that a few more people can join the meeting since it's only you now. So we'll get started in 4 5 minutes so that a few others can also join the meeting. Okay, so I guess more people are not joining the meeting. Like they can join in the middle also. So yeah, so I guess we can get started. So yeah, just to reintroduce myself. So hello everyone. I'm Lakshya Saggi, the problem solving TA for the competitive programming NPTEL course for the Tuesday session 6 to 8 p.m. So this will be our fifth session, and in this session we'll be talking about the topics covered in this week, which were mostly related to graphs, just an introduction to graphs and basic algorithms like breadth first search and depth first search. So yeah, I guess we can get started with graphs there. So I'll just be sharing my screen to share with you guys the problems for today's session. Just let me share my screen. Yeah. So I hope my screen is visible to everyone. So if there are any issues, you can, if there are any issues with the font size or audio quality or anything, you can message on Teams to let me know via chat. So yeah. So otherwise, I'll just assume everything is going fine. So yeah, I guess we can get started there. So the first problem is basically saying that it's consider a simple undirected connected graph G with 65 edges with the least number of vertices possible. Then what will be the number of vertices in the graph G? So the problem asks us that given a simple undirected connected graph. So what's a simple graph? A simple graph is a graph that does not have any self loops or multiple edges between two vertices. So between two vertices, at most one edge can be present. So that's what a simple graph is. So we want to create a simple undirected graph having 65 edges with the least number of vertices possible. So what will be the number of vertices in such a graph? So would anyone like to answer this in chat? Uh, I believe this is a okay. Rahul is saying 66 should be the answer. So Rahul, note that we want the least number of vertices. The 66 would be the high most number of vertices, I believe. So yeah, actually Rahul has posed like your answer has posed an interesting question. So yeah, actually I'm asking about this the least number of vertices. Another question could be the graph with the most number of vertices. So for most the answer would be 66. For the least number of vertices, so the idea here is essentially that we know that in a graph, basically in a simple undirected graph with n vertices. So if we are given a simple undirected graph, then there can be only one edge present at most between any two pairs of vertices. So the maximum number of edges can only be equal to the number of pairs of vertices, right? And number of pairs out of n vertices can be chosen in n choose two ways. So it will be so essentially number of edges in a simple undirected graph will be less than equal to n times n minus 1 by 2. And I hope everyone gets why is this the case. This is because uh, the number of edges will be so the number of edges will be bounded by the number of pairs of vertices, right? Because every pair can have at most one edge between them. And the number of pairs of vertices is just if we have n vertices, we want to choose two vertices out of n vertices. Then there are n choose two ways. So NC2 is nothing but n times n minus 1 by 2. So what we get is essentially number of edges will be less than equal to n times n minus 1 by 2. So just remind you guys if at any point of time if you feel that you have not understood what I just said or like anything in the previous questions, then you can just let me know via chat. I'll try to explain it again. Otherwise, I'll just assume everyone is able to understand everything. So yeah. So for now, we get that the number of edges should be less than equal to n times n minus 1 by 2. So what does this give us? We are given that the number of edges is actually in the graph is 65. So essentially, we are given that 65 will be less than equal to n times n minus 1 divided by 2. So, so basically, when you solve this inequality, it's not too difficult. So n times n, it's just high school maths, n times n minus 1 will be greater than equal to 130. I take the 2 here. So after this, you can see actually that we'll get. So n should be positive because number of vertices is always positive, right? So from this, we'll actually get that. And n should also be an integer because number of vertices is also an integer. So you will actually get that n is actually greater than equal to uh, 12 would be the answer. So yeah. So actually, um, So number of edges is less than equal to n times n minus 1 by 2. And this actually implies that 65 is less than equal to n times n minus 1 by 2. And from this, we get that n is greater than equal to 12. Because you can just see yourself also that at 12, this value of n times n minus 1 by 2 will become something like a 12 times 11 by 2, which will be 66. So 66 is greater than 65. So with 12 vertices, we can make 65 edges. But with 11 vertices, this quantity will be equal to 55. So yeah, so with 55 pairs, we cannot make 65 edges. So that's why n is greater than equal to 12 is the correct answer. So n is greater than equal to 12 is correct. And since we wanted the least number of vertices, so n is equal to 12 will be the least number of vertices. Hence, n is equal to 12 is the least number of vertices possible. So just underlining this. So I hope everyone understands. And so Rahul answer also. So Rahul told the answer 66, but actually that would be the maximum number of vertices possible. So that's also an interesting question. So I'll just leave it to you guys to think about it yourself. I'll just add this here also that try this yourself. So what will be the maximum number of vertices possible? And the answer would be actually what Rahul just said. Answer is 66. So yeah, just try this yourself, guys. This will also be an interesting exercise. So yeah. So I hope this is clear to everyone. So then maybe we can move on to the next question. So second question just says that a simple undirected graph. The second question says that a simple undirected connected graph has 19 vertices. So the graph is connected, it's simple and undirected, and the sum of degrees of all the vertices in G is D. So the sum of degrees over all the vertices is actually equal to D. The number of vertices of odd degree in G is K. So there will be some odd degree vertices and there will be some even degree vertices in the graph. So we are given that the number of odd degree vertices in G is actually equal to K. Then we need to find out what are the possible values for D and K. So before discussing this, I just want to remind you guys of a lemma which has been discussed in the lectures also. So it's called the, I don't remember if it has been discussed by name, but it is called the handshaking lemma. Okay. Yeah. And what does handshaking lemma say? So it says that the number of odd degree vertices in a graph is even. In an undirected graph is even. So yeah. So the handshake lemma says nothing but just that the number of odd degree vertices in an undirected graph should be even. And the proof for this, I'll just remind you guys of the proof also. It's not too difficult. So the proof for this is just that sum of degrees over all vertices, sum of degrees of all vertices is nothing but twice the number of edges. So 2 times m. So m is number of edges. I'll assume n is number of vertices. So I'll just put this here also. So we'll assume. So this will assume in all the questions that n is number of vertices and m is number of edges in the graph. Number of edges in the graph. Okay. So sum of degrees over all vertices, handshaking lemma says that sum of degrees over all vertices is just equal to twice of m. And how do we do this? Because we can say this because in this side, sum of degrees of all vertices side, every edge will come twice. Because suppose there's an edge u comma v, then it will come once in degree of u and it will come once in degree of v. So every edge comes twice. That's why sum of degrees of all vertices is actually equal to 2 times m. And from this, what we can essentially say is that sum of degrees of all vertices is even. So it is always even because 2 times m is always an even number. So this actually means that, so what this means is that, so let's say the number of odd degree vertices, maybe I should just write it down. Let's say the number of odd degree vertices is equal to n1. And let's say the number of, or maybe I should say no would be a better notation because it's odd. And let's say the number of even degree vertices in the graph is equal to ne. So we have odd degree vertices and we have even degree vertices. So what we can essentially say is that uh, the so now what we are trying to say is that we'll try to break this sum of degrees of all vertices into two parts. So sum of degrees of all vertices can be broken into sum of degrees of odd vertices and sum of degrees of even vertices. So I'll just write this down as sum of degrees of odd vertices of odd degree vertices plus sum of degrees of even degree vertices. And now what we can say is actually this. So we know that this sum of degrees of all vertices is even, right? And we can also say that sum of degrees of even degree vertices should also be even because we are counting the even degree vertices here, and sum of even numbers is always even. So this part will also be even, and this part will also be even. So we can essentially say that. So we can essentially say that. Okay. So we can essentially say that this part, sum of degrees of odd degree vertices, it is just equal to sum of degrees of all vertices minus sum of degrees of even degree vertices. And this means that since this part is even and this part is also even, this means that sum of degrees of odd degree vertices is even. Is an even number. So what we actually get is that sum of degrees of odd degree vertices is an even number. And note that the sum of degrees of odd degree vertices is nothing but sum of some odd numbers, right? And note that sum of odd numbers can be even only when the number of numbers is even. So I hope everyone gets what I'm trying to say. So we get that sum of degrees of odd degree vertices is an even number. What this means is that uh, there are some odd numbers whose sum is an even number. And this can only happen when these numbers are even in count. So like let's say we take three odd numbers, let's say 1, 3, and 5. So three odd numbers will always sum to an odd number. 1, 3, and 5 will always will sum to, let's say, 1 plus 3 plus 5, which will be equal to 9, which will be odd number. But let's say we take four odd numbers, or let's say six odd numbers, or eight odd numbers, then this much odd numbers will always sum to an even number. Like 1, 3, 5, and 7 will sum to 7 plus 5 will be 12, 12 plus 3 will be 15, 15 plus 1 16. So that will be an even number. So so what essentially this means, what this implies is that number of odd degree vertices is even. So I hope this makes sense to everyone. And this is what the handshaking lemma says. So yeah. So hence, so just reminding you guys what this handshaking lemma is, and I just discussed the proof because it is quite simple. So yeah, I hope everyone gets it. So we'll be using this handshaking lemma to answer the second question. So second question is asking us that, saying to us that the sum of degrees of all vertices in G is D. So note that it's given that sum of degrees of all vertices is D. And we know that sum of degrees of all vertices should always be an even number, because sum of degrees of all vertices is nothing but 2 times m, which is an even number. So first of all, we get that D should be even. And the second thing is the number of odd degree vertices should also be even. It's given the number of odd degree vertices is k in the problem. And we know, so we essentially can say that k should also be even. So D should be even as well as k should be even. So then the problem asks us which of these values are possible for D and k. So option A is 66, 9, 63, 9, 66, 8, or 63, 8. So I believe now the answer should be clear to everyone. What should be the answer out of these A, B, C, D? Would anyone like to answer in chat? Maybe I should just write down the solution by then. That since sum of degrees of all vertices is equal to 2m, hence 2m equals to D. So D should be an even number. Also, by handshaking lemma, k should also be an even number. So yeah, so Rahul is saying that the answer should be C. So yeah, so C is the only option in which both D and K are even. So yeah, so that's why only C is correct. C is correct because only in C option both D and K are even numbers. So yeah, I hope it's clear to everyone. So after this, we can move on to the next question. Maybe I will keep that in the next page. So yeah. So next problem says that we are given a directed connected graph using an adjacency matrix representation. So adjacency matrix representation, I assume that everyone knows about it. So I'll be assuming that you guys have seen the lecture videos, so you guys know what's a directed connected graph, what's adjacency matrix representation, and everything. So now the problem asks us that for each vertex v in the graph, we want to count the number of incoming edges. So we want to count the number of incoming edges for every vertex v. So I hope so everyone knows, I hope, what are incoming edges and so on. So which of the following is the most accurate description of the complexity of this computation? So we are assuming n is the number of vertices and m is the number of edges, and we want to count the number of incoming edges. The sum of, so we actually want to count the number of incoming edges for every vertex v in the graph. So what would be the complexity for computing this? So note that we are given adjacency matrix representation. Okay, so Rahul is, so okay, so no one is typing in chat. So would anyone like to answer this problem? Uh, Note that the important factor is the adjacency matrix representation. So complexities in graph can change if we are using different sort of representations. So if we are using adjacency list representation, the answer may change, and using adjacency matrix representation, the answer may change, because both of these representations have some benefit or some drawbacks. So yeah. So Rasika is saying that the answer should be B in this problem, which is order n square. So yes, Rasika, so you're correct actually. So good job. So yeah, so the correct answer should be B here. And why is this the case? Because in adjacency matrix representation, for every vertex, if we want to find out what are the incoming neighbors, we'll have to check for all the vertices of the graph whether there exists an edge from that vertex U to the vertex B. So yeah, so the correct answer should be option B, which is order n square. Is the correct answer. And why is this the case? This is because we are given adjacency matrix representation. And so to find the number of incoming edges to V, we'll need to spend order n time. So because we'll need to look at all the vertices to find the number of incoming edges to V, as we need to look at all vertices. So, and since there are n vertices, so overall vertices, this takes order n square time. So overall vertices, this takes order n square time. So yeah, so I'll just underline this also, that option B is the correct answer. Maybe I should not underline, but just bold it. So another thing to note is, what if we don't use adjacency matrix representation, but instead we use adjacency list representation? And for adjacency list, that is the problem in your this week's assignment also. So yeah, so you should think about how the complexity will change if we are using adjacency list instead of adjacency matrices. So yeah. So after this, I guess we can come to the fourth question then. So fourth question asks us that we consider this following graph which is given to us. And now BFS traversal is started from node A on the following graph. So from this node, I hope you can see my cursor. So from this node A, we start a BFS and the nodes are listed in the order they are visited, and which of the following is a possible output. So we want to find out the possible output for a BFS, for a BFS search if we start from the node A. And we are also given that when multiple eligible nodes are present to visit, BFS picks the node which is alphabetically prior. So, so the node which comes first alphabetically will be visited first. So I hope this line is clear to everyone. So using this, I believe this won't be a lot difficult. So let's just see what the BFS traversal looks like. So first we start from A. So how does the BFS traversal look like? BFS traversal. So first we start from A. And now as we start from A, what we'll do is we'll see the neighbors of A. And what are the neighbors of A? Neighbors of A here are B and D. So there are only two neighbors of A. So we'll be adding B and D to the queue. Add B and D to the queue. So I hope everyone remembers what BFS is. We add every vertex to the queue and then dequeue the vertices. And now from B and D, we'll be first visiting B because uh, as we said earlier that B comes alphabetically. So when multiple eligible nodes are present to visit, so B and D both can be visited. So BFS will visit the node which is alphabetically prior, which is the node B here. So now we visit B. Now we visit B. And after visiting B, so we'll add the nodes E and C to the queue. Or maybe you can think of like the notion of tokens, which was defined in the lecture videos, that E and C are also given the tokens. Add E and C to the queue. So I just assume we are using a queue, but yeah. So essentially the idea is we start from A, then the neighbor will be B, which will first get visited. Then we'll visit D. So after this, since B and D were added earlier, so now we visit actually D. And as soon as we visit D, so now we'll add neighbors of D to the queue. And you can see actually that the neighbor E is already added. So we'll not be adding E again, but we'll be adding G now. So we'll only add G now. Add G to the queue, right? So what does the queue look like now? So in the queue now we only have the vertices C, E, and G. And note that C was added first because C was alphabetically prior to E. So now we'll visit actually C. So now we visit C. Now we visit C. And as soon as we visit C, we'll add the neighbors of C, which is F. The new neighbor is only F to the queue. Add F to the queue. And after visiting C, so the next which comes is the node E. So we'll visit E. So now we visit E. And as soon as you visit E now, you can see that all the neighbors D, B, G, and F all had been added to queue prior. So essentially all nodes have been visited, so we don't add anything to the queue. So you can see that G was added to the queue here, and F was added to the queue here, and D and B were added initially. So after visiting E, actually all nodes are visited. So all nodes are added to the queue, so we don't add anything now. No new node added, as all nodes have been added at least once to queue to the queue. So yeah. So now no new nodes will be added. So we'll visit E then, and after that we'll be visiting G, and then we'll be visiting F. So then we visit G, and then so after E we actually added only G, and then we added F. So we'll be visiting G first, and then we'll visit F. So we visit G and then F. So I hope this makes sense to everyone that why are we doing it like this? So we first added B and D. So we'll be visiting B and D after this. So we visit B and we'll add C and E. And now since D was already remaining, so we visit D and we add G to the queue. And now C was visited, then E was visited. Now G and then F will be visited. So yeah. So what's the order in which we visit? So the order in which we traverse is, so what's the order? So we first visited A, then we visited B, then D, then C, then E, then G, then F. So the answer would be something like A, B, D, C, E, G, and then F. So I hope this makes sense to everyone. And this A, B, D, C, E, G, F is nothing but the option D. So yeah. So actually option D is the correct answer. Hence option D is the correct answer. And I'll just underline this also. Yeah. Okay, so Rahul had already written in chat that option D is correct. So yeah, good job, Rahul. You were correct. So so I hope this makes sense to everyone. So we did BFS traversal here. Similarly, in this week's assignment, you have to do DFS traversal. So yeah. So in DFS, there some things will change. But yeah, I hope everyone gets an idea of how to do questions like these. So now the fifth problem is, so we are given a graph which consists of A, B, C, D, E nodes, and these are the edges present. And now the problem says that DFS traversal is starting from node A in the given graph, and nodes are listed in the order they are visited. So which of the following is a possible DFS output? So again, we are given some options and we want to find out which of the following is a possible DFS output. And again, a note is given to us that when multiple eligible nodes are present to visit, DFS will pick the node which is alphabetically prior. So like in BFS, we picked the node which was alphabetically prior. Similarly, DFS will also pick the node which is alphabetically prior. So again, we are starting from node A here. So maybe we can do this question. We can try to do this question orally. So first we start off from the node A, right? And from node A, there are actually two choices to go. So we can go to node B since there are two outgoing neighbors, or node D. But note that DFS picks the node which is alphabetically prior. So from A, we'll first go to node B. And from node B, we'll be going. So there is only one outgoing node from node B. So note that we are doing DFS, not BFS. So after going from A to B, we'll not go to D now. We'll be going inside B. So as soon as we visit B, now we'll go to out neighbor of B, which is just E. So after going from A to B, we'll go to E. And from E now we'll be going to C because C is the only out neighbor. And from C, we can see that only we can get back to B. So we'll not go anywhere further. So we'll backtrack, and then we'll arrive at D again, as all other nodes are visited. So the answer would be something like A, B, E, C, D, which is option C. But maybe I think I went a bit fast, so I'll just. Okay, so Rahul has written in chat that the answer should be C. So yeah, good job, Rahul. You're correct. But maybe I should just write it down for others also. So yeah. So how do we do this? So maybe I should just copy this and maybe make some changes. So this is DFS traversal. So we first start from node A. And as soon as we start from node A, we'll add the nodes B and D to the stack. So in DFS, we maintain a stack. I hope everyone knows this. And in BFS, we maintain a queue. So we start from A and we add the nodes B and D to the stack. And now we visit actually B because we pop B from the stack. And now after popping off B, we can only add E, as E is the only outgoing neighbor of B. So we add E to the stack. And after adding E to the stack, we'll again pop the topmost vertex of the stack, which is E. So we'll visit E then. And as soon as we visit E, the only outgoing neighbor of E is C. So note that I'm doing DFS here, not BFS. So that's why we are maintaining a stack. And now as soon as we visit E, the only outgoing neighbor of E is C. So we'll add C to the stack. And now we visit C and no new out neighbor of C. So as the only out neighbor of C was B, which was already added to the stack. So we see that no new out neighbor of C is present. So yeah. So add nothing. Add nothing. Backtrack. So after this, we again do, so we backtrack from C and we go back to E. We see that like E was already visited, but we see if there is any more out neighbors of E present. And we see that there are no out neighbors of E also present. So we backtrack to B. And again, no new out neighbors of B are present. So we backtrack to A. So actually you can see here that when we see the state of the stack here at this point, so initially B and D were added to the stack. Then B was removed and E was added. Then E was removed and C was added. And as soon as C was added, nothing new was added. So just C was removed. So at this point of time, only A remains in the stack. Only D remains in the stack. Sorry. I hope everyone understands why only D remains in the stack. Because initially we started from A, we popped A from the stack, pushed B and D to the stack, then we popped B and pushed E, popped E, pushed C, then popped C. So only thing remaining is D in the stack. That can be visualized using the backtracking method also, which we say. So now the only remaining vertex is visit D. And as soon as you visit D, so no new node added. Now no new node will be added as all nodes have been added at least one to the stack. So this is the visiting order which we arrived. So we started from A, then B, then E, then C, then D. So hence the order of in which we traverse. So in which we traverse is, so the order is nothing but we start from A, then B, then E, then C, then so A, B, E, C, D. And A, B, E, C, D is nothing but option C. So yeah, which was the option suggested by Rahul also. So good job, Rahul. So I just mentioned this that hence option C is the correct. So yeah. So again, just remind you guys, if there are any doubts, you can ask me, let me know via chat, and I'll try to answer those doubts. Okay. So after this, maybe we can come to the sixth question now. So sixth question says that let G be a simple graph with 16 vertices and 8 connected components. If we delete one vertex from G, then the minimum and maximum number of possible connected components are. So this is a bit of a interesting as well as a tricky question. So I want you guys to think about it a little. That so we are given a simple graph with 16 vertices and 8 connected components. So maybe you can just say that simple as well as undirected. Let's say the graph is simple and undirected, and it has 16 vertices and 8 connected components initially. So I hope everyone knows what connected components is. And now we are allowed to delete one vertex from G. And that vertex deleted will be our choice, and the graph G is also our choice. And we want to answer the minimum and maximum number of possible connected components. So I'll give you guys 4 or 5 minutes to think about it because it's an interesting question. And like try to do this yourself guys and answer in chat. Or maybe like you can also type in chat any ideas which you think and are applicable here, or just some intuition of what should be the correct answer. So try to think about it, guys, for 2 3 minutes. I'll be muting myself while you guys think about it. Okay, maybe you guys can start off with one step at a time. So we have to find minimum as well as maximum number of possible connected components. Let's just say question was asking minimum, not the maximum. So let's say just the question was asking the minimum number of possible connected components. What will be the minimum? So first, let's tackle this minimum one, and then we'll come to maximum. So what would be the minimum number of possible connected components? Okay. So Rahul is typing in chat that minimum would be 8. So uh, Rahul, so you're close to the correct answer, but there is some technicality. So you are off by actually a little bit. So maybe you can think a little more about it. I believe if you have guessed that 8 is the answer, then you will arrive to the correct answer. Like you just need to think a little bit more. So note that we are deleting one vertex from G, and now we are asked the minimum number of possible connected components. Right? Note that the vertex is deleted. Place emphasis on this also. So just think out it. I believe if you have get thought that min would be 8, then you will arrive to the correct answer. Just think about it a little bit more. Okay, so Rahul is asking in chat to explain what is a connected component. A single vertex is connected or just a component? So a single vertex also counts as a connected component, Rahul. Ah, so a connected component is nothing but maybe I should put the definition here. So what a connected component is. So connected component, and we'll be talking about only undirected graph in an undirected graph. So a component C is a connected component of graph G if number of vertices in C is 1. So, okay, maybe I should just explain it like this. If mod C is 1, so where mod C denotes the number of vertices actually. So a single vertex is also a connected component in itself. Or for any two vertices u comma v in C. So this definition, so if mod C is 1, then we are done that it is a connected component. But if there are uh, two vertices u comma v in C such that so if there are at least two vertices in the connected component, then we'll say that it is a connected component if there exists a path between u and v. There exists a path between u and v. So something like this. So do you get the definition of connected component, Rahul? Okay. So yeah, so Rahul is now typing that minimum number of connected components in the problem will be 7. So yeah, that's actually the correct answer, Rahul. Good job. So yeah, so the minimum number of connected components will be actually 7 here. Minimum number of connected components is 7. And how do we get to this answer? So the idea behind is okay. So Rahul, we'll come to the max question later. Maybe I can discuss what's the minimum first, and then we can think again separately for max. So max is won't be 8. It can be more also. So maybe you can think about it while I type out the reasoning for the minimum one. So max can be more than 8 also. So just think about it. We are deleting a vertex, right? And if we are deleting a vertex, that means we are deleting multiple edges. And that maybe can cause a connected component to break apart. So just think along those lines, Rahul, why max can be, what can be the possible value of max? So by that time, maybe we can first discuss the minimum number of connected components first, like why minimum number is 7. So for this, maybe so we are given that we have 8 connected components in the graph, right? So uh, and we are deleting now one vertex from G. So to ensure minimality, what we have to actually show is there exists a graph and a vertex such that deleting that vertex gives us 7 components. And the second thing which we need to show is to show the minimality that no component, like after deleting a vertex, we cannot obtain 6 components. Like because we want to ensure that the 7 is the minimum possible answer. So we have to prove two things. We have to first prove that there exists an example in which we obtain 7 components, and we also have to prove that there can exist no example with 6 components. So first we'll show the existence of 7 components. So how do we show the existence of 7 components? So consider a graph having component C1 to C8. So I'll call the component C1, C2 till C8, C1, C2 till C8. Uh, Such that, so what do we say that all these components, all these 7 components, the C2 to C8 components all have size 1, all have just size 1. So the number of words in the first component is actually 9, and the remaining components have just one vertex each. Ci is 1 for I greater than 1. So note that we'll get 16 vertices using this because there are 7 such components which have one vertex and this has 9 vertices. So there are 16 vertices and 8 connected components. So now let's suppose we delete a vertex. Suppose we delete a vertex from C2. So what this essentially does is if we delete a vertex from the component C2, what does this do? It essentially removes the whole component because C2 just consisted of a single vertex, right? And now we are deleting that whole vertex as it is. So this essentially means that we delete the whole component C2 while all other components remain the same. All other components remain the same, right? So the C2 gets deleted and the components C1, C3, C5 till C8 all remain the same. So we obtain 7 connected components in this case. So yeah, so we obtain 7 connected components in this case. So essentially we have given an example where we obtain 7 connected components, but we also have to prove that this will be the minimum possible. And proving this is not too difficult. You can just see for yourself also that I'll just give this as a lemma, or maybe not as a lemma. Maybe we can show that it can be shown that after deleting a vertex, uh, we cannot obtain 6 connected components. And why is this the case? So suppose we can prove this using something like contradiction. So suppose there was a vertex V in a graph G such that if we deleted that vertex, we were able to obtain actually 6 connected components instead of 8 components. So what this means is that deleting V caused us to remove 2 components, right? And there can be multiple possible cases. So this V, the V which we delete initially might have been a singleton Okay, so maybe I can give you guys this as a proof. Like maybe you can try this yourself. So I'll give you the high level idea because I don't think it's too difficult, and yeah, try it yourself. Yeah. And the hint here is that try to prove by contradiction. So the high level idea is suppose there existed a vertex V on whose deletion we were able to obtain six connected components. So now we'll try to see that after deletion, let's say the six connected components were C1 to C6, then we can check like initially what were the possible connections of V to these connected components C1 to C6. And you will essentially see that uh, if we had connection with one of those any of the connected with any of C1 to C6, then deleting V will not reduce the number of connected components. So V must have been a singleton component. But this would have resulted in only seven connected components initially, which is a contradiction to the eight connected components which we are given. So yeah, that is, consider that there exists a vertex V and a graph G such that G minus V has six connected components, but G has eight connected components. So let's label these six connected components as something. Now show that this cannot be possible. So yeah, cannot be possible. So something like this you'll have to show, and it's not too difficult. So, and how do we show this? Like, this the high level idea is, so you see this vertex V and these six connected components. Now we would have some edges to all of these components. So if V has an edge to any of these components, then essentially the original graph G will also have only six components. So that can't be the case. So V does not have any edge to any of these six connected components, which means that V is a singleton component of its own. But this means that G actually has seven connected components, which is a contradiction to the given statement, which says that G has eight connected components. So yeah, not too difficult, very easy. You just have to, you can just see this via a diagram also. So yeah, so that's how, so we cannot obtain six connected components. And we have an example in which we actually obtain seven connected components. So that's why seven is the minimum. And now comes the second part. I hope this is clear to everyone. So the second part is maximum number of connected components. So what's the maximum number of connected components? Okay, so Rahul is saying the answer to the maximum number of connected components should be 9. So Rahul, actually you are very far off from the correct answer. So just think about this sort of example. So I'll give you guys a hint. So since yeah, since we also have a limitation time, I'll also give you a hint that consider this sort of example which I just gave. That suppose C1 has 9 vertices and C2 to C8 only have one vertex each. And now uh, and now let's try. So we want to find the maximum number of connected components, right? So now try to think what would be a structure of C1 such that if I delete a vertex from C1, it breaks into a lot of components. So try to think of a structure for C1 such that there exists a vertex of in C1 on whose deletion the C1 will break into a lot of components. Or essentially, you can just think that maybe C1 will break into a lot of components of size 1 each. Like every component will have size 1 after removing that vertex. Yes. So Yes, Rahul. So you're on the right track. So Rahul is saying a star kind of component would make sense. So what would be the answer then for the maximum number of connected components? So Rahul is on the right track. Okay. So Rahul is saying that the answer should be 15. So yes, Rahul. So good job. That's the correct answer. That the maximum number of connected components will be 15. And why will this be the case? So this will be the case because again we'll have to show two things. So for maximality, we'll have to show there exists an example in which we have 15 components, and we'll also have to show that there exists no example in which there will be more than 15 components. So first we'll prove the second thing that there cannot exist. So it's also easy to see that there cannot exist an example in which more than 15 components are present. And why is this the case? Would you guys like to point it out in chat? So I'm claiming that after deleting a vertex v from G, no graph can have more than 15 connected components. First of all, let's try to show this. So Rahul, or anyone else maybe would like to answer in chat. Like, so what I'm asking is, why will there not exist any example which can have 16 components after deleting v from G? So, yeah, Rahul. So you're actually correct. So Rahul is saying that this is because there were only 16 vertices initially. So yes. So as there are 16 vertices in G, so deleting a vertex from G, so deleting a vertex V from G will give 15 vertices, will result in 15 remaining vertices. And what does this mean if there are only 15 remaining vertices? So we know that the number of connected components like cannot be more than the number of vertices, right? That's a straightforward thing to see. So as number of connected components cannot exceed the number of vertices, hence number of connected components is less than equal to 15. So number of connected components will always be less than equal to 15. So we have shown using this argument that number of connected components will be less than equal to 15. And now we'll show that there exists an example in which the connected components are actually 15, which will give us actually the maximum one. So now giving an example for the same. Yeah. So again, I'll just copy this example first, and I'll give a structure to C1. And suppose C1 has a star-like structure. And what's a star-like structure? So a star-like structure means that uh, there exists a vertex V such that all other vertices C's of C1 only have an edge to V and not to any other vertex. So I hope everyone understands what I mean by this. So maybe if you don't understand, it's something like this. So yeah, okay, I had these examples. So let's just assume C1 is something like this structure. So suppose this part is actually C1. So you can see that that's what I'm referring to, that there is only one vertex and every other vertex has an edge to only this vertex. So now what happens is actually, so suppose I remove the vertex J from here. As soon as I delete the vertex J, all of these vertices B, G, and C will become singleton connected components in themselves. So actually, this one connected component after deletion of J will become these three connected components individually. So I hope everyone sees this, that this is supposed initially C1, and now I delete this one vertex, then there will be three connected components now. Initially it was one, but then it becomes three. So similarly, so this is on four vertices if C1 had four vertices, but we are saying that C1 has nine vertices here. So C1 has this star-like structure, and yeah. So what this essentially means is that now if we okay, now if we delete V, then C1 breaks into, so C1 breaks into actually eight connected components. Eight connected components. And other components remain the same. And other components remain the same. So essentially the C2 to C8 remain the same, whereas the C1 now uh, breaks into eight components. So actually, so from deleting V, we actually obtain eight components from C1 and these seven components as it is. And other seven components, which were actually C2 to C8, remain the same. So we obtain 8 plus 7, which is equals to 15 connected components. So I hope this makes sense to everyone, that C1 breaks into 8 components and the other 7 components remain the same. So 8 plus 7 gives us 15 connected components in this case. And we had shown earlier that number of connected components cannot exceed 15. So this is actually the maximum number of components possible. So yeah. So I'm assuming this is clear to everyone. So we'll be moving on to next question then. If there are any doubts, you can ask me via chat. So yeah. The next question is just based on application of BFS and DFS. So the seventh question says that suppose you are given a social network with users and their friendships represented as a graph. So basically, uh, we are given some users, and if there's an edge between two users, then they are actually friends. And now we want to find the shortest chain of friends between user A and user B. So we want to find, actually, this basically means that we want to find the path of shortest length between user A and user B. So which of the following algorithms is best suited and efficient for solving this problem? So given two users, we want to find the shortest chain of friends, or let's say the shortest path between them. So this is a very simple question. Like this has been discussed. Okay, Rahul is saying that option B, that DFS should be used to track the distance between A and B. So actually, Rahul, we want to find the shortest distance, right? And shortest distance is found efficiently using BFS, not DFS. So just as an example, just see the graph here, in which we did DFS. While we did DFS, what we did was we initially were at A, then we went to B, then at E. Okay, maybe this is not a good example, but yeah, just leaving this aside. This must have been discussed in the lectures also, right? for this, that BFS, breadth first search, is actually used to find the shortest path between pair of vertices and not DFS. Because in DFS, maybe I can give you an example also where DFS won't give us a shortest path. So how, what example should I give? So something like this should suffice. Hmm. So let's suppose the graph is something like this. Let's say the graph is something like this, and we start the DFS from J. Rahul? Okay, so suppose we start the DFS from J, and now what happens is, suppose we first go to B. So as soon as we go to B from J, so B will be at a distance of 1. And now what we'll be doing is, as soon as we go to B, now we'll be going in DFS to D from B directly, right? So since B was at a distance of 1, so D will be given a distance of 2 now, as we if we go using DFS. But actually know that there is a shortest path of length 1 between J and D, which is just using this edge. So that's why actually DFS does not give us the shortest path. But if we do it using BFS, so while we do BFS, we'll add the all these B, G, and C to the queue first. So these will be visited first and will have a distance of 1. And only after that, and we'll also be adding D here because D is also a direct neighbor. So if we do BFS, then we'll be adding all these vertices at length 1. So that's why BFS will give the correct distance between J and D, which will be 1. But DFS will give a distance of 2, which is actually incorrect. Okay, so Rahul, you got it. That's nice. So that's why DFS, just remember guys, this as a rule of thumb that DFS is never used for finding shortest paths. We use BFS for finding shortest paths. So the answer is uh, breadth first search. And what is the running time of breadth first search? So I hope everyone knows that it runs in linear time. That's good. The lectures also. As BFS is used to find the shortest paths in simple unweighted graph. So note that all edges, no edge has any weight or anything. So maybe this notion will be a bit clearer for the next week. But yeah, let's just say this for now that BF is used to find the shortest path in unweighted graphs. Now comes the eighth problem now. Eighth problem says that in the previous question 7, so we are talking about this question again, the chain of friends one. Consider the friendship information between 8 users labeled from 1 to 8 as given below in the adjacency list. So the friendship information of users is given to us in an adjacency list in this form, right? And now we want to find the shortest chain of friendship between user 1 and user 8, including 1 and 8. So we are given this friendship information that 1 is friends with 2, 3, and 5, 2 is friends with 1 and 7, 3 is friend with 1 and 4. So yeah, note that this friendship will be actually mutual, something like this. So 1 is friends with 2, so 2 will also be friend with 1. 1 is friend with 3, so 3 will be friend with 1. 1 is friend with 5, so 5 is friend with 1, and so on. So we are given this sort of friendship information. And using this friendship information, we want to find the shortest chain of friendship between user 1 and user 8. So how do we proceed for this? We'll first just make a graph out of this friendship information. And in that graph, as we discussed already, we'll do a breadth first search from user 1 and see at what distance user 8 lies. And that will be our answer. So maybe we can do this here only. So I had these nodes as, so maybe I should include more nodes which have. So we'll just make a graph out of the given problem and it will be something like this. So Sorry for this, guys. So this will be the friend 8th. Let's move this here. This will be 7. Let's move this here. This will be 6. This will be 5. So what I'm trying to do is we are trying to construct the graph using the adjacency list first, and then we'll see. Then we'll try to visualize the correct answer. So this will be the second friend, and we don't need this. So these are the 8 friends given to us, and now we know that 1 is friends with 2, 3, and 5. So 1 is actually friends with 2, 3, and 5. So I'll be adding the edges here between 1 and 2, between 1 and 3, because 1 is friends with 2, 3, and 5. And eh, and now 2 is friends with 1 and 7. So 2 is friends with 1 already. So now 2 is friends with 7 also. Right. And now 3 is friends with 1 and 4. So 3 is already friends with 1. So 3 is friends with 4 also. And then we are given that 4 is friends with 3, 6, and 7. So 4 is friend with 3. We already have this as friendship. It's also friend with 6. So 4 is friend with 6. And 4 is friend with 7 also. Yeah. So something like this. And we also know that 5 is friend with 1 and 6. So 5 is friend with 1 and 6. So 5 is friend with 1 already. And we'll say that 5 is friend with 6 also. So maybe we can push 6 here. Yeah. And then 6 is friend with 4 and 5. So 6 is friend with 4 as well as 5, which is already added. Then 7 is friends with 2, 4, and 8. So 7 is friends with 2, 4, and 8. 8 will lie somewhere around here. Yeah. And then 8 is just friends with 7. So 8 is just friends with 7. So this is the graph which we obtain out of the given adjacency list. And now we want to find the length of shortest chain of friendship between user 1 and user 8. So between user 1 and user 8, what will be the shortest chain of friendship? So actually, yeah, so Rahul has already given the answer that the answer should be 1278. So which is the length of it, which is a chain of length 4. So yeah, Rahul, that's the correct answer. So good job. So note that, guys, I played a little trick here. So the correct answer will be 1278, and it can be seen a lot more easily because like I played a trick here that I moved the nodes around so that the graph is easier to visualize. So suppose the graph was a bit messier. Okay. Then maybe it would have not been possible to answer so easily. Like what's the correct answer? What the shortest path between 1 and 8? But like representing the graph in this manner helps us in this. But note that even if it was a bit uh, but note that even if graph was a bit convoluted, still we could have applied the BFS traversal starting from 1, added the node 3 and 2 first, and then while processing the node 2, we could have added like 7, and similarly while processing 3, we could have added the neighbor 4, and you would have followed the procedure of BFS to obtain essentially the answer that the paths will be something like 1, 2, 7, 8 for the shortest path between 1 and 8. So yeah. So sometimes representing a graph more cleanly also gives us the correct answer. But note that this will actually be the graph. This will be the order in which the BFS will traverse. So from 1, we'll first be traversing 2, 3, and 5. Then we'll traversing 7, 4, 6. And then we'll come to 8. So yeah. So looking at the graph gives us an easier picture. So yeah. So answer to this is nothing but first we make a graph. So maybe I'll copy this image also when I upload the solutions. But for now, let's just assume that we already know what the image is. So first we make a graph out of the given adjacency list. Then using BFS, we can see that the shortest chain between 1 and 8 is 1 to 7, 8, which is of length 4. So yeah. So so this will be actually the correct answer, that 1 to 7, 8. This chain will have a length 4 because we have to include user 1 and user 8 both in the length. So yeah. So I'll include this graph also in the final solutions which I upload. But yeah, this is the main idea. So I hope this is clear to everyone. Then maybe we can come to 9th question now. So 9th question says that a directed acyclic graph. I don't know how many of you guys know what a DAG is, but its definition is given here also in the problem, that a DAG is a directed graph with no directed cycles. So what does it mean? So so a directed graph is a directed acyclic graph if there is no cycle in the graph. So each edge is directed from one vertex to another such that those directions never form a closed loop. So I hope everyone knows what a cycle is in a graph. So essentially a DAG is a directed graph which does not have a cycle. It reflects in the name also, right? Directed and acyclic graph. So yeah. So given the directed graph, so we are given a directed graph in the figure, removing the edge E makes it a directed acyclic graph. And now the problem asks us which of the following can be possible values of E. So essentially we are given a graph and the problem asks us uh, which of the edges of this graph can be deleted. We have to remove only one edge, and how many such edges are possible such that removing that edge results in a directed acyclic graph. So essentially uh, from this graph, which edge should we delete so that this graph becomes a directed acyclic graph? So note that this is initially not a acyclic graph because there exists a cycle. This 1, 2, and 4 is a cycle in the graph. So this cycle, so 1 to 2, then 4, 2 to 4, then 4 to 1 forms a cycle in the graph of length 3. So note that this is not an acyclic graph initially, but now we want to make it acyclic. And now we are given some options, and how many of these? So this F option says that this is already a directed acyclic graph. So this F option is already incorrect. But out of these first 5 options, which of the options are correct? Like which of these edges can be removed to result in a directed acyclic graph? So we have to only remove one edge. And what are the possible choices for that edge? So I believe this is a straightforward question. So you guys should also try it. So Rahul is typing that the answer should be 4 to 1. Rahul is saying that if we remove this 4 to 1 edge, then it becomes an acyclic graph. So yes, Rahul, you are correct that removing this 4 to 1 edge will remove this 1 to 4 cycle. And now it becomes a acyclic graph. But is 4 to 1 the only edge, Rahul, which we remove, which if we remove, it becomes acyclic? Or are there more edges which can be removed? Yes, so Rahul is typing in chat that 2 to 4 and 1 to 2 edges can also be removed to make the graph acyclic. So yeah, Rahul, you're correct. Good job. So we can see that actually in this graph, there is only one cycle, which is the cycle of 1 to 2, 2 to 4, and then 4 to 1. So now to make this acyclic, what we can actually do is we can remove this 4 to 1 edge, and you can easily see that if we remove this 4 to 1 edge, the resulting graph becomes acyclic. But in the same manner, we can also remove instead this edge, which goes from 2 to 4. So if we remove this 2 to 4 edge, then also you'll see that the graph becomes acyclic. Note that this 1, 2, 3 is not a cycle because we go from 1 to 2 to 3 in this direction and 1 to 3 also in the same direction. So if there was an edge from 3 to 1, then this would have also formed a cycle. But right now it is not a cycle. The only cycle is here 1, 2, 4. And if we delete this 2 to 4 edge, this 2 to 4 edge, then uh, the graph will be acyclic. There will be no cycle. Similarly, if we delete this 1 to 2 edge, then also there will be no cycles remaining. So I hope everyone can see that. So yeah, so there are three possible answers, which are 1 to 2, 2 to 4, and 4 to 1. So I'll answer this in chat. So note that the graph initially is not acyclic. So is not acyclic as it contains the cycle 1 to 2 to 4 to 1. Now removing either of, so note that this is also the only cycle in the graph, in this graph at least. So we note that removing either of 1 to 2 or 2 to 4, or let's say the 4 to or the 4 to 1 edge, which is results in the graph becoming acyclic. So I hope it's an easy question. So yeah, so what this means is that hence options 1 to 2 is option E, 2 to 4 is option B, and 4 to 1 is option D. So B, D, E are correct. Hence options B, D, E are correct. Yeah. So I hope this is clear to everyone. If this is clear, then maybe we can move on to the next question. Okay, so this 10th question, maybe I can put it on next page. Yeah. So it's easier to see for everyone. So the 10th question says that a house is being rewired, and let's say the house has 10 rooms named A to J. And now to avoid the wires getting entangled and creating short circuits, the electricians have been asked to observe the following rules. So house has 10 rooms, and to avoid wires being entangled, there are some constraints that room A must be rewired before room D and E. Similarly, B should be rewired before D and E. And we are given some constraints that the room should be wired in this manner in the constraints which have been given to us. And now it takes one full day to rewire a room. There are enough electricians to rewire as many rooms as can be rewired in parallel. So note that as soon as so what we want to do is essentially we are given these constraints, and we just want to ensure that these constraints are followed. And on one day we can also rewire a lot of rooms, but we can't rewire, let's say, all 10 rooms at once, because we know that room A must be rewired before rooms D and E. So if room A is rewired on first day, room D and E must be rewired at least on second day. So we can't rewire all the rooms on the first day. We have to follow these constraints. But we also have a lot of electricians. So let's say if we are able to rewire, if we are able to say that we can rewire 3 rooms on one day, then we will have those many electricians available to us. So multiple rooms can be rewired in parallel as long as they follow these sort of constraints. So now the problem asks us, what is the minimum number of days required to complete the job? So actually, I'll just tell you guys the idea behind this problem. So idea behind this problem is something like this, that we can actually represent these constraints as some sort of a directed graph. And in that directed graph, we can try to find the shortest path or something like this. So maybe I should try to tell you guys about this. So let's assume we are given these rooms. So yeah, so these are the rooms given to us, the A to J rooms. And now let's say we add all these constraints. So room A must be rewired before room D and E. So let's say I take the room A and I add the arrow to D. And this A to D, the directed arrow between A to D means that A must be rewired before D. So this is my notation, that a directed arrow from A to D means that A must be rewired before D. And similarly, it must also be rewired before E. So we have another arrow between D and E, right? And now the second constraint says that room B must be rewired before D and E. So B must also be rewired before D and E. So maybe I should just copy these. So, yeah. So B should also be rewired before D and E. And now the third constraint is room C must be rewired before room H. So C must be rewired before H. So this is C and this is H. So maybe I can move these components aside, keep these C and H here. And now this other constraint says that D must be rewired before C and F. So D must be rewired before C and F. So I can put C here and D is here and D is rewired before C. So that's why the arrow comes from D to C. And similarly, the arrow will come from D to F because D must be rewired before C and F. Right. And now E must be rewired before F and G. So E must be rewired before F and G. So E must be rewired before F. We add an arrow here. And similarly, E must be rewired before G. Right. And similarly, F must be rewired before H and J. So F must be rewired before H. So there is an edge from F to H. And J also. So there's an arrow from F to J also. Yeah. And now we also have that G must be rewired before room I. So let's say we move that I here and G must be rewired before I. So I'm just trying to construct the graph here. And then H must be rewired before J. So H must be rewired before the room J. H to J will also be an arrow. And then the problem says that I must be rewired before J. So I must also be rewired before J. So there will be an arrow from I to J as well. Maybe I should make this a curved arrow. Okay. Okay. Okay, I think I am. Okay, maybe we can just put J like this. Yeah. So this is the constraint graph which we have made. And yeah, so all of the constraints have been accommodated. So this is the constraint graph we have made. And now the problem actually asks us that uh, there are enough electricians to rewire as many rooms as can be rewired in parallel, keeping in mind the constraints above. So following these constraints, essentially following the constraints of this graph, uh, we can rewire as many rooms as possible at a time. So suppose this A and B, since A and B do not have any arrow between them, or let's say they don't have any path between them even. So any two vertices, so what I claim here is any two vertices which don't have any path between them can be processed simultaneously in parallel. So A and B here can be simultaneously processed on day one, or let's say on any day. And why is this? This is because uh A and B do not have any path between them, but A and G cannot be processed on the same day because they have a path between them. So on day one, let's say A is processed, then on day two, only E can be processed. And so G can be processed only afterwards. So that's why it won't be correct to process A and G together. So actually, if you guys think about it, what this problem essentially reduces to is actually finding the finding shortest path between all pair of vertices and finding the maximum of all those. So what I mean to say is, suppose I have a path of length, let's say 5 from A to D to C to H to J. So there's a path of length 5 from A to J. Then this essentially means that it will take at least 5 days for me uh, to, if I start from at day one from A, it will take at least 5 days for me to rewire the room J. So room J will be rewired at least on day 5. It can't be rewired earlier than day 5. So if there exists a path of length X in the graph, this will essentially mean that the problem will take at least X days. So actually, yeah. So Rahul is saying actually the answer should be 6 days, but I think Rahul, there's a slight mistake in your answer. Maybe uh, we can see it as we go along. So we know that guys, the path here, there's a path from A to J which is of length 5, right? A to D, then D to C, then C to H, then H to J. So what this essentially means is that J will take at least 5 days. J cannot be done earlier than 5 days. So I don't think shortest path matters here because shortest path between A to J will be a lot lesser. So A to D, D to F, and F to J. But yeah, I think if there exists a path of length X, so yeah, if there exists a path of length X, then uh, we'll need at least X J's, something like this. So if there exists a path of length, there's a path which contains like 5 vertices here. So A, D, C, H, and J. So we'll actually require at least 5 days in the problem. And what we want to find is the minimum number of days required. So note that we have placed a lower bound of 5 because of this path, A to D to D to C to H to J. So there will be at least 5 days required. And note that we can actually do this job in 5 days as well. And what are the 5 days? On first day, let's say uh, so I have drawn the graph a bit cleanly, so that's why it's easier to see. But yeah, so on the first day, we schedule jobs A and B as they don't have a path between each other. Then on second day, we can schedule D and E. Then on third day, we schedule F, C, G. On fourth day, we schedule H and I. And on fifth day, we schedule J. So earlier we placed using this path a lower bound of 5 that we need at least 5 days. And now we have also given a schedule which actually takes 5 days. So Rahul is saying that we are counting layers using BFS. So actually, Rahul, that's what I'm trying to say, that this is not quite true, that we are not counting layers using BFS. Because if we were counting layers using BFS, then J would have been in the same layer as H and I. But uh, this is not quite what we want, because because as I told you that we want to find. So we show that there is a path containing five paths containing five vertices. Even if this is not the shortest path, this path is still a bottleneck. BFS is used to find the shortest paths, right? But we are not concerned with shortest paths here at all. In fact, we would like to find out the longest path instead, or something like this. If you get what I'm trying to say, so we are actually trying to find longest path in this graph and not the shortest. Because if the longer the path, the better the lower bound. So the discussion for finding out the longer paths is for another day. I won't tell you guys how to find the longest path in a graph. In a general graph, it's an NP hard problem, but yeah, let's just leave it at that. But let's just see using our eye test here that I had drawn the graph a bit neatly. So if we draw the graph a bit neatly, then we essentially can see ourselves that there is a path. I'm not saying that this is the longest path. Maybe there was another path, but I don't think there is. So yeah. So there exists a path of length 5, A to D to C to H to J. So there we will take at least 5 days. And we also give a schedule, which actually takes 5 days. And so we can say that our schedule is optimal, that it is taking the minimum number of days. So I hope everyone gets what I'm trying to say here. And yeah, maybe I will remove the 11th question. I don't think it was. It's from the 11th question was what I want to discuss from ungraded assignments, but yeah, I don't think that's necessary. Maybe I'll just write down the solution for this 10th question. So the idea here is to draw a dependency graph of the jobs. And what does this mean? This dependency graph means that for two jobs, let's say the jobs are general X and Y, if X must be rewired before Y, then we draw an edge then we draw a directed edge from X to Y, right? So if X must be rewired before Y, then actually we draw a directed edge from X to Y. So now in this graph, it is easy to see. So maybe I'll call this graph G. Now it is easy to see if there exists a path of length I. So suppose if there is a path of length I, then actually then our then completing all the job will take at least I days. And why is this the case? This is because every job on the path will take one length and there are I jobs on the path. There exists a path. Maybe I should write containing I vertices, path length and this is the difference. Yeah. So I hope this claim is clear to everyone that in this graph G, it is easy to see that if there exists a path containing I vertices, then completing all the jobs will take at least I days. And this is because every job in the path will take one length and there are I jobs on the path. So every job takes one length and there are I jobs. So this due to this path, this will take I days. So now in G, so the G is the graph which I refer to here. I'll add this in the solutions also. So in this G, we can see that there exists a path of length 5. Now in G, there exists a path of length 5. And what's the path? Path is from A to D to C to H to J. A, D, C, H, J. A to D, C to H to J. Right? And this means that completing all jobs takes at least 5 days. So this means that completing all jobs takes at least 5 days. So now that I'm again emphasizing that we want to find the minimum number of days required to complete the job, right? And I'm giving this sort of argument for arguing minimum only. Because the schedule which I gave took 5 days, right? The schedule of A to B, then D to E, then these three, then these will take 5 days. But we want to say that this 5 days is actually the minimum. Like there cannot exist a schedule with 4 days. That's also what we want to argue. And that's why I'm arguing that since there exists a path of length 5, we can't complete our jobs in 4 days. We will take at least 5 days. So for arguing optimality, actually, we are giving this argument that completing all jobs takes at least 5 days. Now we give a schedule. Now we present a schedule which completes, which actually completes within 5 days. So first we showed that completing all jobs takes at least 5 days. And now we will show that there is a schedule which actually takes 5 days. So proving this on its own is not enough, right? That completing all jobs takes at least 5 days. So it may be possible that the jobs can take 6 days, 7 days, 8 days also. A lower bound is 5, but we don't know if it is a tight lower bound. Like if there actually exists a schedule of 5 days. It may be possible that we obtained a lower bound of 5, but actually the jobs take 6 or more days. But in this problem, at least we can show that a schedule exists which actually completes in 5 days. And what the schedule? The schedule is on day 1, we process A and B. And on day 2, we process the jobs D and E. And on day 3, we process the jobs F, C, G, or maybe just I can say that C, F, G for just maintaining alphabetical orders. And on day 4, H and I, and on day 5, J. So yeah. So, and it can be easily seen using this diagram that the schedule which I just gave does not have any dependency issues because we are always going in the downward direction in the arrows. So yeah. So that's why this won't affect the dependencies. Like this follows actually the dependencies, and this schedule actually completes in 5 days. So we present a schedule in 5 days and we show that 5 is a lower bound. So what this gives us is hence the minimum number of days required is 5. So I hope it's clear to everyone that in the second question, the minimum number of days required is 5. So I'll attach these diagrams also while uploading this on the drive, while uploading this document on the drive. But for now, you can refer to this diagram here. So yeah. Okay, so I guess uh, this was the last question which I wanted to discuss. Like There were some other questions which are from the ungraded assignment, but I believe since you already get the answers to those, it is not really necessary to discuss right now since we are running out of time also. Okay, so guys, so I guess this covers the questions for today. So we covered 10 questions today, and you can actually see using these questions like how useful are actually graphs. Like this was a problem which was not related to graphs, but when we use graphs to solve this problem, it essentially becomes much easier. So yeah, so graphs are actually very useful in algorithms and competitive programming. So yeah, so I guess this is it for today, guys. So since we have like something like 5-6 minutes more left, so if anyone has any doubts, any comments, any questions related to anything, you can ask me via chat. Okay, so thanks for the compliments, Rahul. No, Rahul, you're not annoying at all. So uh, actually, I like when people ask questions because then the session actually becomes a lot more interactive. So the more the people ask questions in chat, it's better for me because it keeps the session interactive also. And actually, it shows that you guys are also listening to what I'm saying. So yeah, so feel free to ask questions anytime, and it's not annoying at all. So yeah. Yeah, so if no one has any questions or anything related to today's session or anything else, then maybe we can close today's session. So yeah. So I guess thanks for attending, guys. So I hope I'll see you guys next week also, same time, Tuesday, 6 to 8 p.m. So yeah, thanks for attending today, guys, and hopefully see you guys next week. I'll stop the recording and yeah, goodbye.